Good evening, everyone. Welcome to the third problem. This is DPP3. So this question is on thermal physics, which is on the method of mixes. So a solid piece of chocolate of mass 82 grams is placed on a pan over fire. Okay, the thermal energy is transferred to chocolate at a constant rate. What do you mean constant rate? Which means which is transferred thermal energy. The energy per unit time is seen to be a constant. That's what it tells you. Okay. The graph shows the variation with time t of the temperature of the chocolate at 6 minutes. All the chocolate has got melted. Okay, this is t versus t. So what does this graph tells you? See, the initial temperature here is seen to be, this is I think 35, 34, 33, 32, 31 here. It's 31 degrees centigrade. The final temperature is 45. That means in this region, the chocolate was in a solid state, and from here to here, it was melting from solid to liquid state. This was the melting phase. Okay, and after this, from this point onwards, might be this becomes a liquid phase, right? The specific heat capacity of solid chocolate is 1.6 into 10 to the cube joule per kg per Kelvin. Value of the specific heat is also given to you. So the value of M is given, C is given, delta T can be inferred. What is the value of delta T? 45 minus 31. Okay, so your delta T is equal to 45 minus 31, which will be 5 minus 4 is 1, 4 minus 2 is 1, 14 degrees centigrade or 14 degree Kelvin, both are same. Show that the average rate at which the thermal energy is transferred to the chocolate is about 15 watt. Average rate at which the thermal energy is transferred. So once again, he is asking you the value of E by T, okay, is going to be 15 watt. Now, what is Q1? Q1 is given here. Q1 is equal to MC delta T. M, what is the mass of the chocolate? 4 grams. No, not 4 grams. Let me find out 82 grams. 82 grams, which is 82 into 10 power minus 3 kg multiplied by C. C is 1.6 into 10 to the power of plus 3 multiplied by delta T, which is 14. So when I do this, I get the answer as, where is my calculator? The calculator, right. Okay. So I have 82 multiplied by 1.6 multiplied by 14. So this will be 1836.8. 1836.8. What is this now? Joules, right? 1836.8 joules. And for how long is this been transferred? This has been transferred for 2 minutes from here to here. So therefore, let me write it down here. Right, the power P is nothing but energy by time, which should now be 1836.8 or 2 divided by 2 minutes, 2 into 60, right? On my calculator, oh sorry, this is 0.8, okay, divided by 2 into 60 is 120, 120, so this will give me 15.3. So I get this as 15.3 watt, which is nearly equal to 15 watt as required over here. Okay, now this is asked for 3 marks. Now what do this 3 marks comprise of? How do I write this? The first one is E is equal to MC delta T, and your computation, which tells you 1836.2 watt over here. This will be at least for 2 marks. Now why should it be 2 marks? The reason is because emphasis given for the delta T over here. Many of you will write a misconception here saying that delta T is equal to 45 degrees centigrade. Why is it 45? Why not? Why do we people consider like this? Because the moment you look at this over here, you will consider this is now exactly coinciding at the origin. Okay, that is what is a mistake many of them do, and as a result of it, you are prone to make this mistake. Okay, so therefore, whenever there is a graph over there, see to it that what is the point on the y-axis. Okay, mark the boundaries and then proceed further. Okay, so therefore, now we have got until here, and then what is the next step? We have got this one. Estimate the specific latent heat of fusion of the chocolate. Value of L, he is asking you this one here. Now, what does it say? Once again, it says in the question, if you look at this here, the question it says, thermal energy is transferred to the chocolate at a constant rate. Same rate it is being transferred, which means what? Energy by time taken is same. Now, as a result of it, the same energy by time taken, it is kept on the same heater. The energy by time taken either for this region or for this region is one and the same. If it is one and the same, but what happens is here more energy is being supplied, here less energy is supplied. Why? Because you see the time taken here is 4 minutes over here. Here it is only 2 minutes over. 2 minutes over here, right? So definitely here more energy is being supplied. So what we will do is we will calculate what is the energy there. Now we already got the power, which is energy by time. This is your energy by time is already known to you. If this t value earlier was 2 minutes, now if the t value is 4 minutes, t value is 4 minutes, then this would be 15 multiplied by 4, which would be equal to 60 watts over here. Okay, 60 watts over here. So this is the energy that you get over here, or is the energy being supplied, not watts. Energy being supplied. Sorry, now this is 4 minutes, right? I made a mistake once again. See, that's what happens. 4 multiplied by 60 over here. This should be in SI units. So which will now be equal to 60 multiplied by 60. 15 into 4, 60 multiplied by 60, which should be 3600 joules. This is the amount of energy that has been supplied to the chocolate to melt from the solid at a given temperature to the liquid phase during the phase transition. Okay, this is the amount of energy. Now we know if you supply this much amount of energy, this much amount of energy should be equal to M into L, right? So therefore, we can find out the latent heat of fusion. L should be equal to E divided by M, which should now be 3600 divided by, what is the mass of chocolate? 82 grams. 0.3. 82 multiplied by 10 power minus 3. Okay, once again, let me do this. So I get this as 3600 divided by 82. I get this as 43.90. I write this as 43.9 multiplied by this 10 power minus 3. When it goes upwards, becomes 10 power plus 3. What is this now? L. What is L here? This is joule, this is kg. So joule divided by 8. So in other words, if I can put this as 4.4, 4.39 would be 4.4 into 10 to the power of 4 joules per kg, two significant figures. Why did I choose two significant figures? If you ask me this, here you see this is 3600 has 2SF, this has 2SF. So therefore, I should put this in 2SF. Okay. Remember, this is the way, this is the logic that you need to use to decide what is the amount of significant figures that you are using in your experiment and your calculation. Let me go to the next one. Compare the internal energy for the chocolate at t equal to 2 minutes and at t equal to 6 minutes. Internal energy. Okay. Now, what is internal energy? Internal energy, let me write this as U, is nothing but the energy due to the vibration of the molecules, which is due to the rise in temperature, plus the energy due to the change of phase. I write this as change of phase. Okay. At t equal to 2 minutes, how was the graph? The graph was like this. At t equal to 2 minutes, this was the graph. So what did happen to this one here? So this one, the energy due to the rise in temperature was present, but this was becoming 0 over here, right? So therefore, there's no change of phase. So let me write the energy at 2 minutes. Energy at 2 minutes was just due to E delta T. Okay, E delta T, which is U2 minutes. U2 minutes is so much over here. Now, energy due to 6 minutes. Now what happens? Now here, the temperature of this one is already raised. Okay, so therefore, it has a given temperature E delta T, which I can now write as U2 minutes plus whatever energy was supplied over here. This went in breaking the bonds of the molecules and thereby increasing the potential energy, thereby converting the solid to liquid. So therefore, here let me call this as a U, let us say U only over here. Okay, U potential energy. I'll write like this over here, which means U6 minutes is larger than U2 minutes. See, I have not calculated anything here because you know the command term here is compare. Okay, compare doesn't mean that you need to compute something and then compare. Okay, it also tells you logically you can reason them. So you need not worry about, see, I have not studied about the internal energy expression, or I forgot that one. It's not in the data booklet. No, that's not very much required over here. So you just look at the comparison here. You can just look at these words and you can compute like this. You can determine it like this, and you can say the internal energy at 6 minutes was larger than the internal energy at 2 minutes. Now you are going to reason this. Now how is the mark been awarded? The mark is awarded 1 mark for this one and the other mark for this one over here, and finally you are going to reason this. Okay, but if you write only so much, you will be only given 1 mark. You need to write both of them clearly. Okay, so I think this is the last question for this last part of this question. Yeah. Okay, so with this we have come to an end to this particular problem. So tomorrow you will see the next problem.